Hello everyone. So this is the detailed video about the University of Moratuwa Faculty of Computer Science Engineering Semester 5 project CS2 CS3203 module, and we have given a set of amazing project ideas, and we have chosen to build the event management system. So we call it Ticketly. And before this video, there is a demonstration video in the same channel about this project, explaining what are the functional requirements that we have covered through this project. So I highly encourage you to watch that before this video. So in this video I will go through the architecture and testing results uh, of the system that we are building. So before everything, I'll just have a simple peek at the functional requirement that we had covered through this system. So in our system, we are giving organizers a multi-step event creation wizard. Where that organizer can create set of tiers, and he or she can create sessions and assign seats, create seating maps and everything. And in our system also, we are providing facility to create custom seating charts with different kind of blocks, like non-sellable blocks, which means basically stage and maybe a band. And there are seating blocks which has the actual seats with customizable rows and columns and their labels. Then we have the capacity block, so it is just a block with a fixed number of capacity. And in our system, we have integrated Stripe to simulate the secure purchase flow. So yeah, ticket buyers can purchase tickets in our system. And to prevent the double booking scenario and race conditions, we have used Redis. So I'll explain the implementation of Redis seat locking and details in future. And we are also providing order management facilities. So we have a order service that built with Go to manage these orders and store its detail. And our system have automated email system to notify users when a session is going on sale or when a session is starting, and after he or she have purchased any kind of order and anything. So we have that. And we have the attendee management, which means like if a user is going to attend an event, we have a check-in app built for scanning QR codes and marking that ticket has been already used. So we have that. And for organizers, we are providing options to create discount codes. So currently in our system, we have three kind of discounts, like percentage off, like 10%, 25% off, and we have flat off. It's just a flat number will given as a discount. And we have the buy one get one kind of discounts, where the organizer can select the buy count and select the get count. So for all these discounts, we are providing the facility to set them as public and set the usage limits and set the activation period and many more. So, and for the security side, we have implemented Keycloak as a IAM provider. So we are hosting our own self-hosted Keycloak server in EC2. So in this is with use of this Keycloak, so we are getting like all the advantages of OAuth2 and all of that. And to mention, all the inter-service communications also will be verified with Keycloak. So all machine-to-machine communications are verified with Keycloak. So that way we have enforced the security of our system. Let me check that is recording. Okay, it's recording. Then okay, that's all about the functional requirements. So then we'll move to the next slide. So the problems that we have faced during, the problem we are going to solve during this project is like giving organizers a one place to create, manage, and everything about an event, like seating, payment processing, notification and all. And another problem is flash sales. Flash sales means when an event goes on sale, there will be a lot of orders placed into the system, so we need to handle that. And another problem is like maintaining the transactional integrity of these seeds and entities. Like we cannot allow two users to book the same seat. So that are the main problems that we have encountered during this project, and we have implemented the solutions for this, and we'll see. So to the next slide. So uh, like about this our project, our scenario. So we have let's take an example. Let's say we have 10 organizers. 10 organizers will create certain number of events, and to these events there can be thousands, or like maybe lakhs and thousands, hundreds of thousands of users. So and clearly we have so that there is an imbalance between the write side and the read side of our system, which means like there will be a lesser number of organizers which creates the event, and there will be a higher number of users which will eventually read this event. So if we use a monolithic microservice, so first to mention our architecture is basically microservice architecture. So in this microservice architecture we have integrated this CQRS pattern. So that's what I'm explaining right now. So in the CQRS pattern, what we are doing is we are completely decoupling the write side and the read side of the system, which means we have one microservice which will handle the write to a PostgreSQL database. So then we have another microservice which will consume the CDC logs of PostgreSQL database, and it will populate its own MongoDB, which is optimized for querying and fast reading. So that MongoDB will serve the event viewers, the vast public community. So that's the implementation of CQRS pattern. And to meet the performance requirement of the orders and flash sales, we have implemented our order service using the Go. So Go is very fast and like actually very fast to start up, and very lightweight language, and there are frameworks to build web apps using that, and we have implemented that. And that's it about the architectural pattern CQRS, and I'll explain more about this on the architectural diagram actually. Then as I mentioned earlier, so we have isolated the read and write side of our system using CQRS, and we have used Go for low resource utilization and fast startup. So in this way we can just using Kubernetes HPA, we can scale the pods instantly from a number. Like we can just start up set of pods, like let's say we are at one pod, and we can just instantly ramp up to 8 pods, 10 pods, or anything, like if any kind of spikes happen in the demand. And need to mention that for the query side we are using, for the command side we are using, command means write side we are using Spring MVC, and for the read side we are using Spring Webflux. So Spring Webflux means a reactive framework of Spring. So it is basically not like traditional Spring MVC. It will use the like async loop, that JavaScript kind of system to manage the concurrent requests. So Spring Webflux itself is optimized for maintaining a lot of parallel users. So in that way, with the use of Spring Webflux, we are managing SSE connections, and we are managing the query requirements of public users. Okay, so this is the high level architecture diagram of our system. So I'll explain it using the actual diagram itself because it's a lot easier for me, and I'll explain everything that I have already said. Then just using this image. So as I have mentioned, we have 4 microservices. So we are using basically Java and Go as the languages, and we have the event command service. Command service is the one where organizers actually write the events. Organizers will create their events, and those events will be published to the main event DB, which is a PostgreSQL database. And this PostgreSQL database will generate its own write-ahead login, which we can enable through we can enable WL for any PostgreSQL database. We have this Debezium CDC next, which will capture the logs of PostgreSQL database and publish them to a common Kafka event bus. So we are using an event-driven system. So every asynchronous communication will happen through this Kafka event bus, and for the synchronous communication, we still have to use the inter-service HTTP calls. So any events that are created to this event DB will be published through this Debezium to a Kafka bus. Then we have our event query service, which is developed using Spring Web Flux, a reactive framework of Spring. So it will consume this event and it will do a certain kind of filtering, because in our event DB there are filters that have been rejected from admin. So we don't want them to go into our query DB. So if there is anything that a public user doesn't need to see, it won't be even exist in their database. So our Spring query service will consume these CDCs and populate its own MongoDB. So we are using MongoDB here, and this MongoDB is basically a denormalized version of this PostgreSQL database. So this database is, MongoDB itself is optimized for heavy querying. So users can query using a lot of parameters, and there is inbuilt support of like geospatial indexing in QueryDB, which means like we can search for a location and with a radius, then we can find events within that radius. And MongoDB itself is optimized for querying and reading. So we are using a MongoDB here to serve the public traffic. Then about caching, so we are using Redis for the caching basically. And event command service, we are basically caching the ownership info. Ownership info means in our system, if you have seen the demonstration, we have few entities. We have events, we have sessions, and we have organizations. As hierarchy, we have organization at top, then we have events, then we have sessions. So if organizer is going to change any of these, change, create, update, or delete any of these entities, we have to check the ownership of these entities. Even though, not even like if he is going to access these information like analytic information, and when he going to update these things, when he's going to delete any of this. So in every case we have to just check the ownership of that entity. So we are caching that ownership because that's that ownership checking will be happening so frequently in the admin dashboard. So because of that, we are caching that ownership information. So in that way, we don't have to bother our PostgreSQL database every time when organizer is trying to view something or delete something or edit something. So that way we have reduced the load to our event DB. And for the event query service, we are caching basically the trending informations. Trending informations means if you have seen in demonstration, we have this trending counters and these trending events. So no one will ever consider, like no one will ever notice whether these things will update every 6 hours or every 2 hours. So because this counting events and counting tickets, we don't have to do this every time when a user log into our homepage. So because of that, we are caching these frequent informations. And about the cache eviction, because we have carefully designed the places that we have to evict our cache, so there won't be any invalid information in our home page or anywhere because of the caching. So cache will be evicted automatically when something changes. So basically for these counters we have a TTL set, so this will be automatically expired within 6 hours, and then system will calculate this again and show to the user. And that's about the event query service. So then we have the ticket/order service. So this is the place where we are storing ticket information and order information for the events. So when a user is going to purchase a ticket, he will be directly connected to this order service, and in there we will do validations and everything that need to be processed when an order is placed. So I'll explain the order creation flow on a later slide. So for now we are using Redis to manage seat logs. Seat logs means, so when a user is going to purchase a ticket, we are going to log that seat for a certain duration. Right now the system timeout is set to 5 minutes, so we are going to log a certain seat for 5 minutes, and if the user haven't completed his payment with that 5 minutes, we are going to expire that payment, and we are going to release that seat so other user can book that seat. So for this service we are using a PostgreSQL database to store the informations and ticket informations. And this microservice will also like publish the changes happening to the seats. Like when a seat is being locked, this microservice will publish it, and our event query service will consume that event and stream to the user. So we are using SSC connection managed through event query service because Spring Web Flux is optimized for managing such a lot of SSC connections and such like a lot of parallel requests, not like traditional Spring MVC. So that way we are letting users to know live when a seat is getting locked and when a seat is getting booked, and so on. So then we have the scheduler service. So as I already said, we are deploying these microservices in a Kubernetes environment. So in a Kubernetes environment, every pod is burstable. I mean, they can die anytime, and they are getting recreated. So if anything happens, so in that case we cannot hold any state within our microservice. So as you know already, Spring and other microservices will inbuilt support for like background scheduling and everything, but we are not using that because we are deploying everything in a Kubernetes environment, and we want these microservices to be stateless. So in that case we are using like in our system we have a scheduled notification system where we notify users. Subscribers means the people who are interested in a particular entity, like an event. We will notify them when a session is going on sale, when a session is going to start. So to store that subscription information, we are using this PostgreSQL database, and to schedule things we are using AWS Event Bridge. So when event get created, already the BCM will publish the change happened to that entity, and we will consume it here too, and schedule the notifications. I mean, we are putting a basic event bridge schedule saying that this event is going to start on this time, and then when that time comes, the event bridge will put that to SQS, and our scheduler service will consume it from SQS and send it will get the list of emails that is subscribed to that entity and send them. So that's how the email service is going to work. And we have already implemented this using Go, because this microservice will continuously poll the SQS, and not actually just short polling, or we are long polling the SQS, which is the recommended way of getting information from SQS. So that's the AWS recommended way. So we are long polling the SQS for 20 seconds and getting the schedules, and if a schedule comes here, we are sending emails. That's about the core microservices. And then we are, as external services, we are using S3 bucket basically to store files, and we are using keycloak SIAM. So keycloak will authenticate every internal machine-to-machine call, and also keycloak will authenticate the every users call using OAuth2 and JW token and so on. Then for the third-party services, we are using Google Analytics and Stripe. So Stripe is to process payments, and Google Analytics is to manage the analytic informations about events, like number of views that particular event getting, and number of where those people are watching that event, and main traffic sources, whether those traffics are coming from WhatsApp or whether those traffic are coming from Instagram and so on. To calculate those things, we are using Google Analytics. And in here we before implementing everything in Kubernetes, we had the API gateway, but we don't need the API gateway anymore, because Kubernetes itself has a ingress controller which can basically route the traffic. And front end is pretty obvious, like we have a mobile app, and we have mobile app is basically to scan QR codes. It doesn't serve any more purpose, it will just build to scan QR codes. And everything like sales and browsing happens through our web app. That's it about the basic architecture. So then let's move to the next slide. Okay, that's the previous slide. Okay, so as I have already explained, this is the event approval data flow. So as you have already seen in the demonstration, a user will need to create an event and admin have to approve that. So after an admin approval, so the BCM will capture that change in the database, and then our query service will, DBCM will capture it and publish to the Kafka, and our query service will consume that and create that denormalized document in MongoDB, and then our users can basically see the event. So I hope that's clear. And one thing that is really important for a system like this is to prevent conflicts in seat reservation. So this is the critical point that we need to address. We need to avoid users from booking same seat. Avoid two users from booking the same seat. That's basically the problem we have to address. So let's see what are the solutions that we taken to mitigate this scenario. So this is a rough diagram explaining the seat lock flow. So you can I'll just explain this once and go in detail. So when our order service will get a request saying that this user is going to place an order, our order service will receive that request, and then it will be try to lock that seat in our Redis using its setNX method. And Redis itself is a single threaded system, so Redis will ensure that the same key won't be accessed by two threads at the same time, through threads or through two ports. Like as I have already said, we are deploying this system in a Kubernetes environment, so there will be a sets of ports that are running. Like maybe in a flash sale scenario, it can ramp up to 8 ports, so there will be 8 order microservices running, and Redis will ensure that only one microservice will access this key at one time, because Redis itself is very fast. That won't be a problem that won't be a bottleneck at all. Then if a seat is already locked, other user will notify that this seat is already locked, and he can place order, and the one who acquired the lock is the acquisition winner, and he can just lock the seat and proceed towards the payment and go forward. So that's the rough order placement flow. And since this is a video and you have the option to pass forward and skip anything, I'll go through the actual seat validation flow. Okay, so this is the flow happening in our order service. So first we are, when request hits the order service, we are going to check the authentication, whether this user is authenticated and available in system. And this will be done via key clocks. And if user is authenticated, then we are moving to next step, so which is the check seat availability. So in this step we are just checking whether the seat is already locked in Redis, and if seat is available, then to the further steps we need to get a machine to machine authentication token. So if that token is available in the cache, we are using that m2n token, because we need to call the event query service to a validation check whether the seat is valid and whether the seat is available in the system. So we are doing this first validation with event query service, because event query service itself is designed for the speed. So it's a very fast call, because looking up something in the MongoDB is real fast. And if that seat is validated, then validated and that seat is available, then we are going to log that seat in Redis. So after this step, the critical part is over, and there is a user that owning this particular seat. And now we are moving to the more heavy and writing based part, where we will do like the heavy stuff. And then we are defining a rollback. So this is something that we need to go do in Go. So, and next we have the final seat validation. So we are doing this with our command service. So this command service is built with PostgreSQL database, and it will be particularly slower than event query service. Not much, but it will be a little bit slow. That's why we are doing this second validation after this critical step has been passed. And we are doing this second validation because if there is any kind of delay of data propagation, and if there is any kind of data, if the data in command database and query database differs, so in that case we need to we don't need to book that seat. So that's why we are doing this second validation. And then we are basically calculating the price, and if there is a discount we are going to apply it. And if everything is okay with that price, if the price isn't negative and we are just validating things, and if everything is okay with that, we are publishing the seat locked event to the Kafka, saying that the seat is locked. Then our event query service will consume it and stream the SSE event, so other users will see that the seat is locked live on their screen. Then we are going to do the saving steps, and we are going to create tickets, and we are publishing order created event. And so this order created event will be consumed by our notification service, and it will send the notification saying that user, you will have this order, you need to complete with this in 5 minutes, and otherwise it will expire, and so on. So, and we will respond to the front end with an order ID. So in the meantime, we are creating a payment intent with Stripe. So that payment intent will be created with the price that we calculated in the backend, and then we will return a specific payment intent ID and its secrets to the front end. So the front end can use the Stripe's payment interface to do the payment. So after successful payment, Stripe will call us through our backend. So Stripe will let us know, Stripe will let our backend know whether this payment is completed or not. So we are not taking anything from the front end, and we are using a Stripe webhook for that. And so this flow is over. Then after payment completed, we are just marking that seat as booked, and that seat won't be available for any other users to book. So in any case, seat unlock happens. So after a timeout, or if any error occurs, we will just basically cancel that payment intent. So during this step, if anything wrong happens, we will in the final step we are creating the payment intent, so we don't have to cancel the payment intent if anything happens above that step. But in a timeout situation, if a seat is timed out, we are going to call Stripe through our backend and say that this payment intent isn't valid anymore. So the user cannot proceed with the payment because it is expired. And user will also see it in the front end because there will be a countdown in the front end, uh, still he or she can proceed because we are doing any validation in the front end about order expiration, and we are just directly calling the Stripe and saying this payment is expired. So there is no way that user cannot proceed with that payment. So that's the standard way of doing online payments, and we are following that in our system too. So that's about the order creation flow. Then okay, before that, as you have seen, we are locking the seats in Redis. So if a user has abandoned these seats, if a user is not going to book these seats will be unlocked automatically after 15 minutes. So I'll just explain the unlock mechanism of these seats. So there is an actual observation that we have seen in that system, and we have implemented a solution for that. So let's say this is our Redis, and this is our Go microservice. And one more thing, so this is not about seat locking. So this is not about seat unlocking, this is about seat locking. So about seat locking, our first idea was to use a queue, like to avoid double booking scenario, use a queue. So queue would be nice if we are having a single instance and a single thread processing these orders. So we thought about scaling this horizontally. So when we are going to scale this horizontally, this queue won't be like, this queue won't serve any purpose. I mean, like, if this message got consumed by this microservice, this will be instantly consumed by this pod. So these are all the order service pods running. So using a queue won't prevent anything of like double booking and everything. So this will consume the order request 1 to, let's say, seat 1A, and this one is also going to try to book seat 1A. We cannot guarantee that who will succeed, or we cannot guarantee, I mean, maybe most probably both will succeed because of like because I mean we are completely depending on this queue. So if we are using a one thread, then this will be safe. This will be safe because the second request will be processed after that first request. So when we are going to scale the system horizontally, that queue won't do anything. So that's because we have used Redis for that seat locking. So that to be mentioned. And about the seat unlocking, what I was going to tell is, so let's say we have 3 pods running the order service. So when the seat is going to be unlocked, we aren't polling the Redis itself, because polling the Redis, checking whether this seat is unlocked, and that would be huge overhead. So Redis is sorry, Redis itself has a feature sorry for that. So Redis itself has a feature called Redis key space notification. So this Redis key space notification will notify, I mean, will broadcast the event saying that when a certain key expires. I mean, we are setting a seat lock for, let's say, 5 TTL. So after that 5 minutes passed, then this Redis will be broadcast the message saying that this seat is unlocked. And the problem is, this is a broadcast. So this seat unlock event will be published to all these 3 Go pods that are running order service. So the solutions that we had was, the one solution is we have to use another microservice just to consume this broadcast and publish it to Kafka. So in that way, this Redis can just broadcast to that one microservice, and it will put it to the Kafka. Then our one of the Go microservice will consume it. I mean, Kafka itself is handling the horizontal scaling scenario with partitions. So that's the option one. The option two is that what we have implemented. So we don't need the overhead of building another microservice just for this scenario. So we have implemented a semaphore kind of system. So this event, this after this seat unlock event is broadcasted, let's say it first goes processed by this order service. So it will put another key to the Redis saying that it is unlocking this event. So that's basically like a semaphore. So it will say that it is unlocking the seat 1A. So when this event got consumed by another user, another pod, it will also check whether this key exists, and it knows if another pod is unlocking that seat. So then it will, I mean, this pod will basically ignore the message. So in that way, we are ensuring that only a one seat unlock will be happen, because if we didn't go for anything like this, what will happen is eventually the same seat will be unlocked by these all three pods, and it will be 3 seat unlocked message published to the Kafka. Then there will be a system imbalance, because there is a little time window where, like, let's say we have this is our 3 seat unlocked event. So if the same broadcast consumed by these three, if we didn't implement any kind of this semaphore kind of system, so if this seat unlock event consumed by the event query service, then that seat is basically unlocked and this seat is available, and if someone else is try to book that seat, so this is a seat booking, then he or she might get succeeded. I mean, he will succeed, he will book that seat because that seat is unlocked. And then this query service, after this, if this query service consumes this second seat unlock event to the same seat, then it will be do SSA stream saying that this seat is unlocked. We are handling, I mean, we are not allowing in the backend, we are not allowing to unlock the book seat. So a book seat cannot be unlocked, but the SSA event still will be published, and there will be a certain level of inconsistency happening in the events. So basically we need to maintain that atomicity when we are going to unlock a seat, which means, so when we are going to book a seat, that will be automatically happen, because Kubernetes will only exactly send the seat booking request to one pod. But Redis, because of this Redis is broadcasting this, we will use this semaphore kind of system. So if one order service pod is unlocking this seat, then other pods won't even touch that thing, and it will just ignore it. So in that way, we are ensuring that only one seat unlocked event will be published to the Kafka. So that's about seat unlocking. And as I have said, we have done this all, we have taken these steps to mitigate this double booking scenario and everything. So we aren't just they aren't just words, we have actually tested that. So now I'm going to show the test report. So at first we have tried with this is what we have tried. So I'll explain it. So we have a event with 16 seats, and per seat we are creating 100 virtual users. So basically these are like 100 users try, and we are calling the order service to book that per certain seat. So this will simulate 100 concurrent users booking a seat. So one seat will be, I mean, 100 users will try to book a one seat, and if everything works correct, only one user would be able to book this seat. So that's what need to be done, and we have actually tested that, and here are the test results of that basically. So we have done this test using K6. So K6 is a testing tool provided by Grafana, and as you can see, we are hitting 1600 requests, 1601, because this one is to acquire JWT token to authenticate a user. So let's just ignore that one, and we are hitting 1600 requests, which means 100 per seat to book a certain seat. And what we are actually observing is there will be only 16 successful bookings, which means there are 16 seats and there will be exactly 16 successful bookings. And we can see 1584 bookings have been failed. So we can see that we are achieving that thread safe double, we are avoiding that double booking scenario, and we are maintaining the accuracy of the system. So that's the test that we have done to ensure that a seat won't be booked by two users. So, and actually, so that's what we have presented in the final presentation. So before a hour or two, I have actually tried this with 1000 users. So as you can see, the 1000 means 1000 users will be trying to book the same seat, and there will be 1000 requests coming to the system saying that this seat is going to be booked. I'm going to book this seat, and as you can see, this scenario also, we are getting only 16 successful bookings, and we can see like we have 15,984 seat locked. We have 15,984 errors saying that this seat is already locked. So the system is successfully handling this much of a load. So we are hitting like 1000 requests per seat, and we are getting this result. So that's actually pretty good, and we have mitigated that double booking scenario and all the challenges that we came across that. So that's it about the double booking scenario, and this is actually the actual K6 report. So as you can see in here also, we can see the 16 successful bookings, and this is for that 100 per seat scenario, and in this report they are somehow rounding this number. So this actual number is 1584 seat locked, so failed, and only 16 have been successful. I can you can skip this. So, and I can also test this again, show that this system is working, and the system is handling this kind of load. I'm going to run the test again, and we have this is the event that we used for testing. As you can see, we have 16 seats, and to simulate the actual concurrent scenario, I will just disable the HPA. HPA means horizontal pod auto scaling, because I'm going to manually scale the number of order service pods running, because if this thing has been already activated, then it will be automatically scaled out the system, because our system is designed to handle much more load, so this isn't much load. So because I'm just remove this HPA policy, and I'll manually scale up the number of ports in order service. So let's say we have, let's keep for like, let's say we have 4 ports, and you can see the ports are being created, and we have 4 instances of order service currently concurrently running, and now they are up, and there will be resource utilization will be shown in minutes. Here, let's wait till they appear, to be exact. Okay, now they're here. So we have 4 order services, 4 ports of order service running. So there will be that exact scenario where request will be consumed by all. Kubernetes will Kubernetes will load balance the request to these 4 order service ports. So so what I'm going to do is, now we have 4 order service ports, and the client will be try to book these seats, and all HTTP requests will be evenly distributed across these 4 microservices, 4 ports. And what we are going to do is, we are going in this seating map, we are going to hit 1000 requests per seat. So it's a scenario where 1000 users trying to book the same seat, and as we expected, only one should succeed. Let's see. Okay, so we are setting the parameters to 1000 users, and we are running the test. And in the meantime, you can see these seats are being lively locked. So the reason we have this 1 second delay is because in order to get a HTML report output from the K6 itself, we need to have at least running the test for like 30 seconds, because we are intentionally keeping a delay of 2 to 3 seconds between each lock. So otherwise this will be instant. We can just book the 16 seats instantly. So as you have seen, we have hit 16,000 requests, 1000 per each seat, and we can see there are 15,984 failed bookings, which means only 16 have been succeeded. So this ensures that our system is handling that double booking scenario and concurrent seat handling very effectively. Okay, that's about that double booking scenario and handling the concurrent orders. So I'll just commit. So these are the reports, HTML report, and this is the JSON report. So I just commit that so I can use it later. Okay, that's about seat booking. And this presentation was made with when I have done the testing with 100 virtual users. Now I have done it with 1000 virtual users, 1000 people trying to book the same seat, and you see we are still getting the same accuracy that we are expecting from the system. So our system is designed to handle that much of a load. And I will just enable that HPA, Kubernetes HPA that I have disabled, because we don't have to run like 4 ports of order service every time, and Kubernetes will automatically scale them when a load comes. So I'll just enable the HPA again. Do we have the command now? Mm. Okay, now the HPA is configured. Now, okay, now we are down to one pod, and Kubernetes will automatically scale this pod when a flash sale scenario comes. Okay, that's it about that. Now, why I'm going backward? Okay, now we are going to move to the deployment section, where I'm going to show how we are handling the thousands of simultaneous requests with Kubernetes HPA, and how we are managing the load. So for the deployment, we are deploying everything in AWS, and we are using 5-node K3s Kubernetes cluster. So K3s means K3s is a lightweight Kubernetes implementation, and we are using RDS for database, and we have Redis, and we have S3, and we have SQS and EventBridge. And Kubernetes itself will provide the zero downtime, because then that non-functional requirement will be automatically satisfied, because Kubernetes is designed to maintain the zero downtime within updates and everything. So we are guaranteeing that high availability. Okay, so this is the deployment diagram. So I'll explain the deployment diagram also with the draw.io. It's much easier. And about the deployment, just to make sure I'm recording. Testing, okay. Yes, I'm recording. Now it's 54 minutes long. Oh my. So this is deployment we are having, and currently everything is deployed in AWS, and we are in the region of AP South 1, which is Mumbai, which is closest to Sri Lanka. And in AWS we are basically having 3 public subnets and 3 private subnets. So I am in this diagram, I have merged all of them because I mean for my easier demonstration. And basically we have 3 public subnets and 3 private subnets. So, and in our private subnet we have our Kubernetes worker nodes. So we have our 4 EC2 servers with 2 GB RAM each and 2 vCPU each. So this 4 worker nodes will handle the load. These four worker nodes will actually handle the microservices running in them. So as you can see, we can show them in the cluster. So this is a Kubernetes cluster, and we have 5 nodes. So this one is our control plane, and these 4 are the actual worker nodes. And then in our private subnet we have our RDS. So RDS is in the private subnet, so no one can access it from the outside internet. And we have this another EC2 instance to host these infrastructure components like Redis, MongoDB, Kafka, and Debian. So this is built to host that infrastructure component. And then in the public subnet we have ALB load balancer, which will distribute the load web traffic load to these 4 worker nodes. And before the load balancer, I have implemented the WAF AWS firewall to ensure that there won't be any DDoS attacks and so on. And this is our kubectl master node. So this is the place where we are executing all the Kubernetes control commands. And the best practice is to host this in the private subnet, but since this is a university project and we are not going so much serious, we are deploying this Kubernetes master node in the public subnet itself. And we have our EC2 authentication server. This is also an EC2. And we have our net now. So this net gateway will provide the required internet connection for the components in the private subnet, and we have the internet gateway outside. So that's, and these are VPC, so that's obvious. And we have our S3 bucket, SQS, and even bridge outside, so they aren't belong to a certain VPC basically. And that's the deployment diagram we are having. And one thing to mention, to run the system in idle, we don't need this much of worker nodes. I mean, see our system, I can show the resource utilization. So as you know, we have like for our system we have 10 GB of total RAM, and currently we are using only 2.6 GB. So we can run the system with 2 ports with actually a heavy load. So for the demonstration purpose and for testing with extreme load conditions, I have just deployed with I am running the system with 4 worker nodes. And that's about the deployment. And one thing to mention is when we are managing this kind of AWS deployment, so we cannot just create everything by hand. So we are using Terraform to basically code our infrastructure. In that way, we can just create everything, and we can just create everything in an instance and destroy everything and do updates and everything. So we are using Terraform for that. And about security, we aren't just allowing every port and every IP address to the EC2s and to the database. We are actually filtering, and we are only allowing the necessary ports and necessary IP addresses to each deployment component. So as an example, this EC2 instance will only have the ports required for these microservices to access, and this EC2 instance will only have the HTTPS port and port 64434 for kubectl traffic, and this RDS instance will only accept traffic to PostgreSQL database only from this security group and this security group, and those kinds. So those are the basic security steps that we have taken to ensure the system is secure. And that's about the deployment. And for the monitoring, by the way, I'm using OpenLens. So in the OpenLens, I can just monitor our Kubernetes cluster very much easily. One thing to do later is we can implement, if it's better, we can implement something like Grafana with Prometheus to collect logs and everything. For now, we are just using OpenLens to just view logs and everything. And that's it about the deployment. And this is the actual load testing that we have done in our system. So I'll just explain them also using the reports itself. That's actually helpful, I think. So as you already have remember, we have a query service. So even query service will handle all the query traffic to the system, and we are simulating the exact flow of a user log into the home page, and user going to view the trending events, and user is going to view an event, and user is fetching CT map. So we are simulating that flow, and we have done the load testing with up to 2000 virtual users. So this is the load test that we have done with the one query service port, and this is what we have done with the multiple ports. So as you can see, when we have a one pod of event query service running, the system will basically, with the load, system will have a response time of 1 second, and after the virtual users have been increased to like 1.5k, we can see system is going to throttle down, and eventually there will be some HTTP request failing. So this is what happening if we are using a one pod. So that's why we are implementing horizontal scaling with Kubernetes. So as you can see at this point, our system is completely failing because we are running on limited resource and everything. So then with the horizontal scaling activated in Kubernetes, we can see our system. So there is a little spike of failed requests right here because this is the place where the horizontal scaling actually kicked in and start up the other pods. And then you can see we are maintaining the request rate of, in here we are maintaining a request rate of 500 requests per second, and we are maintaining a response time of 49 milliseconds. In this also we are ramping up to 2000 users, and in here we are at the request rate of 1000 requests per second, so 1000 core requests per second, and we are maintaining a response time of 34 milliseconds. That's actually really great. And we are hitting like 1000 requests per second and maintaining that 36 sub 50 millisecond response time. So that's actually a strength of Spring Web Flux also itself, and with the Kubernetes horizontal scaling. So as you can see within this test, we have run this test for like 7 to 8 minutes because we cannot afford more, because ALB is going to charge us for the data transfers and request count. So we have transferred 1.05 GB of JSON data, and our system is basically maintaining 50 milliseconds of response time with this much of load. And one thing to mention is so this is the event query service, and we can see this event query service itself is currently using like 500 megabyte of RAM, and we are allowing the horizontal scaling up to 5 pods. So we are up in the maximum, with the maximum load we are like we are basically hitting like 3 GB of RAM usage, 3 GB of RAM usage of this event query service with the maximum usage, with the maximum limit. So, and we are maintaining this sub 50 millisecond response time. So then another aspect that we need to test is our order service. So order service is the place that actually orders will be getting. And one thing actually interesting is, as you can see, this service is written in Go, and in the idle scenario this one is only consuming 13 megabyte of RAM. So that's actually really interesting. That's the one of the main strength in Go, that really low resource utilization and RAM footprint and everything. So we have tested that order service also with single pod. So this is the test result that we have gained with a single pod running. So when a single pod running, you can see we also beginning with 500 users, and we are ramping up to 2000 users. So right now at the beginning we are at the request rate of 500 orders per second, and we are getting a response time of 1.7 millisecond and so on. Not like a Spring microservice. Actually this even a single pod of this Go microservice, we can see it is quite well handling like 500 requests per second with even a single pod, and it is having like 3 seconds of response time. So after this, you can see after we are exceeding the 500 requests per second, we are getting basically throttled down. We have our request duration increasing. Now request duration is like 7 seconds, and now the requests are failing, and that's the scenario. So when we hit a limit of like 500 requests per second without horizontal scaling, one microservice will basically fail. So with horizontal scaling on, which is actually our system, as you can see, we are like hitting basically 3000 orders per second with 500 milliseconds of response time. To be mentioned, this order placing order flow is consists of certain steps of verification and everything, because in that case we are at least should be expected 500 millisecond response time. And as you can see, with even 2000 orders per second, our system is holding 1 second of response time when creating an order. So that's actually really great. And about the horizontal scaling policies, for the order service, we are allowing to scale it up to 8 pods, because as you have already so this order service is consuming like in the heavy load scenario, it will consume like 100 megabytes of RAM. So we can just scale it up, like we can scale it up even for like 10 pods, and it will still consume a RAM of 1 gigabyte. So we can just, for this test itself, I have scaled the system to like 8 pods. So on the maximum load, it will be running parallel 8 pods. And for the previous event query service test, it will be running with 5 pods at max load. And for the scheduler service, we have 3 pods. So in a peak emails, I mean, if there are so many emails going, then there will be like 3 pods of scheduler service running. And as you know, event command service, we have, because of that imbalance, and we have less number of writing to the less number of event creation that than reading, we are only scaling up that to 2 pods. So that's about the load testing. And in last, our system can easily handle 2000 orders per second. We are talking per second, so it means like 2000 means more than 120,000 orders per minute, I think. So system is designed to handle that much of load. And to be mentioned, this is only with 5 pods, and this each pod will only use each pod will only have 2 gigabytes of RAM. So basically, for the workloads, we are basically having 8 gigabytes of RAM and 8 CPUs, and we are handling like 2000 orders per second. That's actually really great. Okay, now let's see the HPA in action to see how the system scale ups with orders. So I'm going to run this exact same test again with hitting up to 2000 virtual users and like hitting up to 2000 requests per second, 2000 orders per second, and see how the system scales up. And let's have a look. So I'll run the test, and before running the test, I'm setting the number of virtual users. I mean, this is the base count, 1000. So it will be like first start at 1000, then it will be 1.5 times of this, so 1500, then scale up to 2000. And right now you can see we are running only 1 pod for the order service. And I'll turn on the kubectl HPA monitoring. So because this OpenLens is showing some kind of delay when displaying this CPU matrix and information, just run this. So in here you can see the thresholds that we are currently at. Okay, now I'll run the test and see how it goes. Okay, now getting test is running, and people are trying to book seats, and some of them are booked and some of them are booking them, and the system is now it's at 1000 virtual users. It's hitting 1000, and let's see. Okay, now we are using 200 times of threshold, and you can see 4 new ports have been spawned to serve the load, and now they are serving the load. and so on. The test will continue. So okay, now to mouse point. Where is that? Okay, yeah, and they aren't serving it yet, so they'll serve the load heads up, and that's the system handling the load. And I'll stop the test right here because ALB is going to charge us, I think, for the number of requests coming in and going. So as you can see, we are like now at almost 200,000 requests have been completed, and because we are, I mean, because actually we don't have this much number of seats, we are retrying for the same seat. So that's why you are seeing seat already locked message right here. And I'll stop the test right now. Okay, and as the results, you guys can see we haven't run the full test, and you can see we are having a response time of 300 millisecond average. That's actually really good. So that's about the load, and that's about the load testing. So these are the same results that we have already seen, like for the query service, and this for the order service. And then I need to mention about system actors. Our system will have an event organizer and ticket buyer, ticket staff, and system administrator. So I think you have seen these four users in the demonstration video, and this one is the keycloak admin. So this is the one who with access to the keycloak admin dashboard. So he will be have the uh, all the access about users. I mean, he's the one who managing the users, so he can just lock out the users, he can add admins, he can create admins, he can remove admins, and so on. And that's it about the project. And this is our team. So I am Dasun Jitung, and I have our mate is Rumani Jesuri. So without being him, we won't be able to build such a concurrent and such a performance system. So I want to thank him and everything for everything. And then we have our mentor, Mr. Dakshita Suryarachi. So Dakshita have been guiding us with everything, that every problem that we are facing, and like he's been helping us a lot to successfully complete this project. So our special thanks to Dakshita Suryarachi. Dakshita, thank you very much. And that's it. And I'm going to skip the live demo because we have already uploaded the demonstration video, so you guys can proceed with that. And that's it. And thank you, have a good day.